This is CPM Calculus Chapter 2, number 117. So here we're told if h of x is equal to 4/5 x cubed minus 2x plus 5, use sigma notation. Oops, that does not look like sigma. Use sigma notation to write Riemann sums to approximate the area of h bounded by the x-axis between 10 and 15. So the area bounded by the function h and the x-axis with 10, 20, and 100 left endpoint rectangles of equal width. Then use your calculator to find these approximations, okay? Compute with the calculator, and then what happens as the number of rectangles increases. So explain the change. So we're going to get different answers for each. Okay, so let's start this. We know we need rectangles, right, of equal width using our left endpoint. So whatever our function looks like, we're going to start at 10 and go to 15, right, and our curve from here to here, and we're going to put rectangles in between, right. Left endpoint means we look at that point, create them on the left, right. But this right here is 1, 2, 3, 4, 5, but we need 10, 20, and 100. So to get 10, we're going to have to break this up. So we know the distance between 10 and 15 right here, the distance is 5 units, right? So to break 5 units up into 10 places, we're going to have the width equal to, for every one of these rectangles, if there are 10 of them, so for 10, is going to be 5 units divided by 10, or 1/2. Okay? Okay, and that makes sense because if we have 5 units, and we put 2 within each unit, then we get 10 rectangles. Okay, so the width is 1/2. So then the area over here, remember, is approximately, because this is the actual area, but we want to approximate, is approximately, we're going to start with some letter, k, and k is equal to 0, 2, and we need to do 10 of these, so from 0 to 9, right? We always do 10 minus 1 gives us 9, and then we just multiply the base times the height. Well, the base is just the width, so we know the base is 1/2, right? And the height is our function h of x at what? We know it's going to be h of, so h, our function at where? Well, we're going to start at 0, right? And then we're going to add in what each time? We're going to basically add, so we're going to start at 0. Well, not 0, sorry, we want to start at 10. And each time we want to add 1/2. So we want to add 1/2 times k. Okay? So this is going to approximate it, but we can't put it in our calculator like that. We need to plug in and get rid of the h, the function h, and actually put in h of x for what it is. So we know it's going to be from k equals to 0 to 9, 1/2, and then h of 10 plus 1/2 k is going to be 4/5, and then here we have our x, so it's 10 plus 1/2 k cubed minus 2 times, again, x, so it's going to be 10 plus 1/2 k plus 5. Okay, and let me close the parentheses there because we opened it here. It's going to be that times 1/2. Okay, so let's put this in our calculator and see what we get. Okay, so turn on our calculator, and so how do we get the sigma? Again, we start and we go to our catalog, and it's at the end, or at S, right? It's at the very end. Oops. Oh my goodness. There we go. Okay, so here's our sigma notation. Here we put the expression, the variable, low and high. So our expression is this whole thing here. So it's 1/2 times 4/5 times 10 plus 1/2 k. Well, instead of k, I'm just going to use x because it doesn't matter. Cubed, right? Minus 2 times 10 plus 1/2. Instead of k, I used x. Close the parentheses there. Plus 5. Close, close, I believe. And then the next thing we do is say comma, and our variable is x. Our low is 0, and our high is 9. Right, we're going from 0 to 9. Oops, too few arguments. Okay, what did I do? So you look here, and I want to make sure that I have all my parentheses. So I have 2 on the right here. This one closes this one. There's another open one. 1. Okay, so I have too many parentheses over here. So I just counted them, and I have 1 extra closing it. So I can delete that, and I try. Okay, so is that how I want it to look? 1/2, yep, from x is 0 to 9, 1/2 times 4/5 times 10 plus 1/2 x cubed minus 2. Yes, this looks just like that. Okay, so that's equal to that. And let me get approximately. So that's approximately, well, it's hard to see. That's 7,558.75. And we know we're looking at area, so units squared. Okay? So that is using 10, right? 10 left endpoint rectangles. So let's move down our calculator. And let's look at 20 and 100. Okay, so to find 20, let's do it in green. What are we going to change here? Well, using 20, right? So using 20 rectangles, we're going to change the width, right? So the width now for 20 is 5 divided by 20. That's 1/4. Okay, so then our area is going to be now from x equals 0 to, let's use k, because we're going to have h of x. Anyway, from k equals 0, and now we're going to 20, so 20 minus 1 is 19. And the base now is going to be the width. The base of every rectangle is 1/4. The height is going to be times h of 10 plus 1/4 k, right? Because we're starting at 10 still, but every time we're going to add 1/4 and get that y value, or h of our number value, okay? So when we plug that into our function, we're going to have k equals 0 to 19, 1/4, and then we plug in our function here, so h with the input of 10 plus 1/4 k. So here we are, so we're just 4/5 times this cubed minus 2 times this plus 5. Okay, so it's going to be 4/5 times this cubed minus this, which is 10 plus 1/4 k plus 5. Okay, so if you look and compare these, this changed to 1/4, this changed to 1/4, and this changed to 1/4. Everything else is the same. Let's put it in our calculator. So I could just use this and change all those 1/2s to 1/4. So 1/4, 1/4, and 1/4. And also my low is 0 and my high is now 19, right? So I'm going to change my low. My low is still 0, but my high is 19. So I do that, it calculates that. So let me get the approximate value. And that right there, it's hard to read again, but is 7,790.3125. I'm reading it from there. Okay, so that's using 20 rectangles. So now we have to use 100 rectangles. Okay, so for 100 rectangles, right, I know we're going to go from k equals to 0 to 100 minus 1 is 99. And the width is going to be 5 units divided by 100, or 1 over 20. And so it's going to be 1 over 20 times 4/5. We're just plugging into h of x. 10 plus 1 over 20k cubed minus 10 plus 1 over 20k plus 5, right? So let me cancel that out because we don't want it there. Okay, so this is our function to find using Riemann sums to calculate using 100 rectangles. Okay, so the difference between this one and the previous one now is just we look at the same function, but instead of our endpoint being 19, it's 99. And then also instead of 1/4, we're always going to change that to 1/20th. And that's 3 times 1/20th. Yep, there's the last one. Okay. Oh, it's getting slower. So here, okay, it looks good. We can scroll and make sure it looks how we want it. Yes, yes, yes. And then let's just approximate this. And that's approximately now. Come on, calculator. Okay, it's hard to read, so I'm going to put it in this place. So it's 7,977.8125. Okay, and again, this is units squared. And over here, we also had units squared. I forgot to write that. Okay, so we did part A. Okay, we did part B, was saying now then compare 10, 20, and 100 rectangles. So is our answer the same each time? It goes from, so with 10 rectangles, we have the approximation being 7,558.75. With 20, we get 7,790.3125. And then with 100 rectangles, we get 7,977 as our approximate area. So you might think, oh, when we increase the number of rectangles, maybe the area increases. But that's not true. Remember, when we're approximating area under a curve or whatever, the more rectangles we use, right? The more rectangles we use, the less wasted space, or the less the less area we're going to not account for. So the more rectangles we use, right? If we use a rectangle here, a rectangle here, like the more we use, the less area we're missing, right? Because we're using more, so we're approximating better. So as we increase the number of rectangles, we're actually getting a better and better approximation. And that's because our approximation is approaching the actual area, right? As we put more and more rectangles in, we're getting closer and closer to the actual area under the curve. Okay. So this ends CPM Calculus Chapter 2, number 117.